by construction, that's what that is. But here's a straight up formula for it, for our finite dimensional linear. This business here this has application in infinite dimensions and operator spaces and such. So we will talk some about that in here as we need to, but I try not to talk too much about it because, you know, it's a little bit beyond the course, generally speaking. But so there's our M. So how does that? So I guess we need a theorem, right? We need a theorem that if the limit of f1, well, excuse me, if f1 is bounded, no, that's not even what I want. Oh yeah, fine. Well, I don't want to use f1 though. Let's say if g1 is bounded at phooey. If g1's bounded, I'll use a different letter here altogether. If g1's bounded at p, and the limit as you know x goes to p of g2 of x is equal to 0, then the limit as x goes to p of g1 of x star g2 of x is in fact equal to 0. I mean, that's a theorem we can prove. This is like a Calc 1 theorem that if you have a function which is bounded and you're multiplying it by another function which is limit 0, it implies that the product of those functions limits to 0, right? So we could prove that here as well. Man, it seems like I'm not going to get the partial derivatives today. If I prove this anyway. How should we prove? Can we prove that? Let me erase some space under here, see if I can prove. Do you agree if we can prove that theorem, then my product rule follows? Yeah. I never actually wrote the product rule either, did I? What is it though?
Differential of f1 of p times f2 of p.
Yeah.
Plus the differential of f2 of p times f1 of p.
Now when I write this formula, it has to be with the understanding that when we evaluate that on h, it feeds h into the differentials, and we have to, let me just write of p here so there's no. But yeah, that's the product rule. Now, okay, so what are we up against here? We're trying to show that the norm of g1 of x times g2 of x, right, is, we want that to be less than epsilon, right? And what do we get control of? We have, norm of x minus p less than delta, right? Now, I'm trying to think. But the girls are giggling in the hallway. It's not helping me. I mean, this means that we can make the norm of g2 of x, right, to be less than epsilon, whatever epsilon we want, right? So certainly we could make this is minus 0, right? We can make that less than this, right? So, all right, so let me say it's bounded by, let me do big K, okay? Bounded by big K. Is it bounded by M? Bounded by M, fine. All right, so my point is that this, here's the thing. I used M for a different reason. We had a formula, right? That if we had the product of two vectors, then this was less than or equal to, remember what it was? Like let's call it M sub star, right? Remember this? Like I built a constant based on the product that makes the norm of the product less than or equal to that constant of the product times the product of the norms, right? Okay, great. The point then is that this, by assumption, is less than M star. G1 is bounded, so that's M, right? But this one, we can make, right? We can make that strictly less than the product of this, and epsilon over those two things, because we have continuity at 0 of the other guy, which makes this epsilon. So that the proof is let epsilon be greater than 0, choose delta greater than 0, such that this implies that G2 of x is less than epsilon over M star M. Then by the product inequality we proved the other day, in this estimate we have that is less than epsilon, epsilon being arbitrary, we proved that the limit's 0. Yay! So we proved the product rule. I think the proof that's currently in my notes is not this. I think the proof that I have currently in my notes is a coordinate-based proof. It's calculational, and that's probably better for like engineers who take my class and stuff, but I like this, like what we did today. All right, so let's talk about the partial derivative. We'll finish there. At least I'll introduce the partial derivative. All right, so how do you define partial derivatives on a vector space, right? How do you find partial derivatives on a vector space? Well, so first I have to deal with an issue. Well, I'm just thinking about something right now. What's up?
Sorry.
No, go on.
We need component functions.
Yeah. No, actually, no. We can define it independent of the component functions, actually. The issue is, in Calc 3, when we talk about directional derivatives, we insist on a unit vector. However, when I studied advanced calculus, I first studied Edwards' advanced calculus, and he has a directional derivative which does not presuppose a unit vector, which means that it doesn't quite describe the rate of change exactly, because it's not normalized. So I'm debating. Well, anyway, the definition I currently have on page 57 of my notes, I guess I better stick with. Here's the definition, and I'll fix it. I'll fix the definition in a second here. dvf of A. I'm going to put a P there instead of an A. Is equal to the limit as h goes to 0 of f of P plus hv minus f of P over h. Notice here h is a real constant. It's not a vector limit. So this is the so like in Calc 3, I've been talking about this lately. And the formula I gave for it is this, right? It's like here's typical Calc 3 stuff. But you notice there's an assumption that this is a unit vector. Well, at least in Edwards' advanced calculus, he does not make the assumption that it's a unit vector. So I don't think I will either. All right, so so if I wanted to, so I mean, I just this in my notes on page 57, right, of my 2015 advanced calculus notes, definition 3.2.1, I presuppose that the function is a function from Rn to Rm, right? But this definition makes just as much sense if we're in, if our function is a mapping from, a vector space V to a vector space W, like that. Okay. Now, yeah, I do think, now, so, I would say partial derivatives. Well, I mean, you could say that this is partial f, partial v at the point P. Some people would say that. It's the rate of change of f in the v direction at P, which is itself described by a vector in W. I mean, this limit, if it exists, it's a vector in W, right? Now, but usually when I talk about so anyway, I think it's if V is, let's say, the span of V1, V2, Vn, and we use x is equal to like x1 V1 plus xn Vn, so like, in other words, phi beta is equal to x1, x2, xn. You can view those as the coordinate functions of phi beta, I think. I think that makes sense. Here I'm defining like, it's kind of silly, but I'm misusing notation a bit here. I'm saying x sub I hits x, and guess what it gives you back? It gives you back x sub I. So like I'm defining, here I'm thinking of x sub I as a mapping. Here I'm thinking of it as the values of the map. This is a typical abuse. We do this in calculus. Like we use x both for the arbitrary point, but also for the, all right. Now, so then with this notation, if I was to say partial f partial, xi, that would mean the differential, well, the directional derivative in the vi direction, right, of f. And of course, we got to talk about a point. So no, I don't, but you notice I don't have to talk about component functions here. It's just in the domain I'm doing funky stuff. Let's see here. So let me give you a weird example. Or example of what? What example are we on?
Because basically we need a basis.
Now, it is true though. It is true. A basis for the domain, yeah.
Although we can define a partial B where B doesn't have to be in the basis.
That's true, yeah. So obvious questions that we want to answer. We want to understand what is the relation, if there is any, between these directional derivatives and the Fauché derivative. Like if the Fauché derivative exists, do these directional derivatives exist? How about the other way around? If all of the directional derivatives exist, does the Fauché derivative exist? That's what we'll talk about next time. Let me just try to give you an example here. Are we at example, am I on 4? 3? I don't remember.
3.
3, okay. Let me do something pretty weird. Let's do like f of a equals to a squared. Where here I'm looking at f as a mapping from R2 by 2 to R2 by 2, right? And so of course A is what? It's like A11, E11, plus A12, E12, plus A21, E21, plus A22, E22. So I'm thinking of the A11, A12, A21, A22 as these are the coordinates on the space, right? They're coordinates with respect to the usual unit matrix, right? So in that regard, I can calculate what is partial f, partial, like A11, for instance, at a point, at a matrix P, right? So I would calculate the limit as h goes to 0, right, of what? I'm supposed to do P plus HV, which would be H, let's see here, the basis correspond, that's E11. I'm supposed to square that, because that's my map. And I'm supposed to subtract P squared from that. I'm supposed to divide by H. Then the question is, how does that go? So let's see. Well, that is the limit as h goes to 0 of, we've got P, E11.
When we say A11, we really mean E11.
Huh?
When we say A11, the coordinate, we really mean the partial with respect to the basis.
Well,
elements, right?
you notice that this would be equal to, in my notation.
Yeah.
So yeah,
Okay.
fair enough. Yeah. So I've got an h here, right? And then I've got plus HP. My bad. Let me try this again. Multiplying this out, we got p squared plus HPE11 plus HE11P plus HE11 H squared E11 squared minus p squared, all divided by h. Now we got to think about how matrix multiplication works, right? Like, what was our rule? If we had EIJ times EKL, how'd that go? It wasn't it Kronecker delta JK EIL, I believe. So when I do something like P times E11, that's equal to like the sum over I and J, right, of PIJ, EIJ times E11. And if we think about that, the only way that I need the J to be 1 for this to be non-zero. So I have to put J equals to 1. So I get like sum over I of P I1 E I1 E11, but this is, of course, that was actually what E P I1 E I1, which of course is P11 E11 plus P21 E21. The p squareds cancel, so I get and the h. So like you notice that there's an h on this term, so I think I get P11 E 1 plus P 21 E21. That's just from the from this term, because that's what I calculated over here. Now so these cancel, and this of course limits to 0. So you're just, I mean, well, fine. You know what? Let me not be so descriptive. I mean, this one I'll just write as plus E11P, right? In other words, what we had here was just PE11 plus E11P, which we of course could, you know, you could sort through that more. I showed you how to, this is that, you know, but details don't. The point is, there is and the partial derivative is what? It's a it's a matrix in this case. Now, the the question is what's the, well, we figured out last time that the differential of this was what? Good question. Oh, good point, good point. Thank you. So what we figured out last time that D sub PF of, let's say, H, right? What was it? It was, in my current notation, pH plus HP. I mean, we had an A here instead of a P. That does look, so look, this would be what? This would be the differential. Oh, thank you. Thank you so much for saying that, Ernesto. This would actually be the differential of F at what? H equal to what? E11. Right. That is not an accident. That's actually the theorem. Yeah. That if the differential exists, the differential at the basis will be equal to the partial of the basis.
So the differential implies that all the partials exist.
That is true. Yeah, differentiability implies all the partials exist, but not the other way around, unless we have continuous differentiability of all the partials, in which case we can prove that continuous differentiability of all the partials implies that you can put them all together to build the Frechet derivative. Yeah, that's hopefully what we'll prove next time. We did it in 2 dimensions in the other course, but we should do it in N here. Anyway, thank you.